All right, so this is the notes for the one lesson in Chapter 10 that we cover still. And there's 3 parts to the chapter, but we just covered the last part, which is really looking at some notation about what it means to create composite functions, which essentially means putting one function inside another. Really, really important for understanding parts of calculus, and another thing that we will use throughout the course. And so in general, the first thing you see here, these 3 expressions all mean the same thing. And I'll start actually with this one. If you look here, we have function, this literally means function g is the input to function f, so a function inside a function. And another way of showing that is like this, and that's not it's not an O or a 0, it's a symbol for a composite function. And so the way we'd say that is f of g of x, and you can also have brackets around it. So all these 3 things mean the exact same thing. In this case, function g is inside function f, and the order matters. And so let's first just get a little bit of practice with this notation. So this time, let's call function f x minus 4. Let's call function g x squared plus 4. So this first example on the left, f of g of x, I would recommend first rewriting it as g of x inside f of x, just to make it more clear. Okay, that's literally what it means. So what is g of x? G of x is x squared plus 4. And all that's inside f. And so function f now, if I look back up here, what does function f do? Function f is very simple. You take whatever the input is and you subtract 4. And so right now my input is x squared plus 4. So from x squared plus 4, I want to take, if I want to write the equation for it, it'd be x squared plus 4 minus 4. In this case, that's what all function f does. And that's because function f is so simple. It's just x minus 4, which means your input take away 4. So in this case, I can see my 4's cancel out. And so f of g of x, that composite function, the quadratic function inside a linear function, this particular one in the end behaves the same as just x squared. It simplifies down to x squared. And so now if I want to find f of g at 4, I have a few choices. I could first rewrite it like this, f of g at 4. And I could, if I want, take g at 4, figure out what that is, literally go back to my equation up here, replace x with 4, and then take that number, whatever I get, and put that inside function f. You know what, maybe I'll do that. So you know what I mean? So g at 4 is 4 squared plus 4, which is 16 plus 4, which is 20. So that's what g at 4 is. And so now 20 is what goes into f. And again, I put 20 into here, and all f does is take away 4 from whatever your input is. This is 20 take away 4, which is 16. However, notice, I've also, because I already found the equation for f of g right here, I could have just taken that 4 from the start and put it into this equation right here. Because that equation, x squared, tells me what this composite function f of g does, and so that would have been faster because I found this equation. That said, neither is wrong. And so I'll get rid of all this spaghetti of red lines, but it's all the same thing. Okay? And so for this, g of f, which is the other way around. And so for this, I will first write it like this, just in case that's helpful. Function f again is x minus 4. So I'll just write x minus 4 right here inside function g. Function g is x squared plus 4, which means the input of g is squared, and then we add 4. So the input is x minus 4, so I'll take x minus 4 and square it, and then then add 4. And so if I do that, I have my equation. Now, if you're tempted to expand and simplify x plus 4 and combine like terms, basically you would take it out of vertex form. Right now I have a quadratic function in vertex form, and I can put it in general form. But one's not better than the other, so I'll just leave it like this. Okay? That's just my function in vertex form. Vertex form, as we know with quadratics, is quite useful for a lot of things. And so now, if I want to find g of f at 4, all I really need to do is take that 4 there and put it right in that x. Right? I don't actually have to literally input 4 into f and then into g. And so I'm going to just take that 4 right away, like I mentioned before, and put it in there. And so I know this must be the same as 4 minus 4, all squared plus 4. Well, that's a pretty pleasant equation to deal with, which is 0 squared plus 4, which is 4. Now again, if I hadn't already figured out this equation right here, it would be totally fine to figure this out. To first put 4 into function f, which you get out of 0, then put that 0 into g, and obviously you get the same thing we just did. All right. So the main really thing about that was understanding the notation. So now I just want to show you what happens when we combine functions in different ways. And we've already seen from the previous example, if you combine them in different ways, you get different functions. And just kind of have a bit more practice with it. And also realize, if I look at this last one right here, you don't have to combine just two functions. You can put a function inside itself. There's that bell. All right, that's not for us, though. All right, so first of all, let's look at these two functions here. F of x is a linear function. I can tell by looking at the slope and the y-intercept that the equation of this is x minus 1. The slope is 1, the y-intercept is negative 1. Function blue is a radical function. We've been seeing those in chapter 2. And so I can tell this looks congruent to root x, but translated 1 to the right, so it must be root x minus 1. All right, there's function f and function g. So for all of these, I want to find the equation. For the first one, f of g of x, I want to find the equation like we did before. I want to simplify it, and then I want to sketch it, and then I want to state the domain and range. So let's look at f of g, which again means f of g inside. I'll put g in blue. So again, g of x, I found the equation. The equation for g of x was root x minus 1. And that's going inside function f. And function f is just x minus 1. The input take away 1. So this is going to be the same as root x minus 1. I'll write it like this and keep my color coding going. Take away 1. Now, I can't really simplify this anymore. I can't put these two subtract ones together because one's inside a radical, one's not. So I'm done. I have my radical equation, which I can now visualize quite nicely. I can see this is congruent to root x, except translated 1 down and 1 to the right. And so I'll draw this in, draw this in green. So I'm going to take root x minus 1, take away 1. So I'm going to visualize root x and move it 1 to the right and 1 down, and I know that's what f of g of x will look like. So it'll be right here. Now I can draw this quite quickly because I have a pretty good sense about what root x looks like, and I hope you do as well. And once I draw this, right, that's f of g of x, or right here. I can now see the domain and range quite nicely. I can tell by just looking at my graph, the domain is greater than 0. Sorry, take that back. The domain is greater than or equal to 1, and I can see the range is greater than or equal to negative 1. Oh, and I just realized I'm only asking for the domain. Oh, then I'll just write down the domain. All right. So I would actually recommend you try these next two on your own. Pause the video before I do too much more. It's the same sort of idea. But I'm just going to carry on. And so for the next one, I'm going to rewrite, as usual, this in this notation. So this means g with f inside it. And I'll put f in red to match the image above. And so in this case, it's g of x minus 1. And what does function g do? G, remember, is root x minus 1 itself. So for g, if I want to take this, I want to take the root. My input is x minus 1. Take away 1. Now in this case, these two take away 1s are like terms. I can put them together. So I have root x minus 2. And now I can visualize this line, and I can see the domain. I can see this particular function, which is the same thing I had before. I just reversed the order of the composition, so it definitely made a difference. I can see root x minus 2 is going to be congruent to root x, but 2 units to the right, and that's all. So I'll draw that right now. So it's going to start at this point, and then assuming we can visualize root x quite quickly, we can draw this quite quickly. There we go. And I can see the domain of that is anything greater than or equal to 2. And just notice again, I'm taking the same two functions. Oh, I must be sleepy right now. I just realized my domain for the previous one, I put negative 1. What's going on here? Please forgive me. If you don't, I guess, what can I do about it? And let's get to the last one. So the last one is g of f. So first, what does that mean? That means we take function f, and we stick it inside function f. Actually, I'll make these color-coded. So we take function f, and we stick that inside function f, and we stick that inside function g. That's what it means. So what does f of x mean? Well, that means I have x minus 4 for the inside function, and all that's inside f again. And again, function f, all function f does is it's x minus 4. It's the input take away 4. So if the input is x minus 4, more bells. Thank you. And so if the input is x minus 4, I'm just going to take away 4 from that again. So this will be x minus 4, take away 4. What is wrong with me? X minus 4? Oh, I apologize for the 15th time in this lesson. This is what happens when I make a video on a Friday morning. I think my brain just wants to take a break. Sorry, f of x is not x minus 1. It's not. I'm just going to take a little sip of coffee here. Gotta admire the empty room. Take a deep breath. All right. I think I'm ready to go again. Let's go. All right, so instead of f of x, it's x minus 1. And so this is going to be x minus 1. Take away another 1. Phew! Which is x minus 2. And that's what's going inside g. And again, g takes whatever you put inside it, you root it, minus 1. So it's x minus 2, take away 1. And so in the end, it's root x minus 3. Well, that took a little bit longer than it should have to get there. And I can honestly take a function and put it inside itself over and over and over and over again. But in this case, I can now visualize this as being a radical function translated 3 units to the right. And so I can see the domain then must be, before I even graph it, I know the domain must be x is greater than or equal to 3. And I'll draw it up here. All right. So with that said, the most important part of all of this is just getting a sense about how to read this notation. And at that point, you're really just using what we learned at the very beginning of the course, which is understanding function notation, the idea of putting, expressions inside functions, and hopefully not screwing up as much as I did. All right, so that leads me to the final problem. I mentioned before that this sort of idea of understanding composite functions is crucial for calculus. And what's crucial in calculus is that you can look at a fairly complex function and visualize it, imagine it as being a composition of functions. And it's without teaching calculus, it's a key idea for an essential idea for part of the course. And so what I have here are 4 functions. I've given you the graphs, and all of them are compositions of exactly 2 of these. Okay, so function A, B, C, and D I have up here. And so for all the 4 graphs you see below, they're all created by taking 2 of these functions and putting them together in some order. And again, the order usually matters, but just 2. And so for this first one in red, which I can see starts right here, there is no single equation up here that creates this graph. But there is a pair that when you compose them together, when you put one inside the other, will create this. And so your goal is to try to figure that out. As usual, I would recommend you just try this on your own for a bit and then check. And so I would just pause the video. But this first one, if I look at the equation of it, it does look like a radical function. The good thing is we've learned about radical functions. So just by looking at it, I can see the equation of this looks like root x, but translated 3 units up. And so if I look at my choices up here, root x is right here. And x plus 3 for A means my input plus 3. So I need to combine these 2 together. And in what order, though? I want the plus 3 to be separate from the radical. And so in this case, I need to put c inside a, not the other way around. So this needs to be y equals a of c of x. Or you could write it as a of c of x. I don't really care which one. I kind of like the first one better because it makes it more clear what's the inside function. The second one is a bit faster to write. And notice, if you look back at my choices, if you take function c, root x, and stick it right there, you have root x plus 3. And that's the idea for all of these. If you do it the other way around, though, if you take x plus 3 and put that inside here, you get a different function. You get root x plus 3. The plus 3 is inside the radical, which is actually a translation 3 to the left, not 3 up. So in this case, and in most cases, the order matters. All right, so at this point, I'll just kind of give the answers for these next ones. So this one here, which by the way, I can see the asymptotes, which I'll just draw. And even though we haven't yet gone into detail about these types of functions in this course, we will soon. And asymptotes are kind of a key characteristic of it. But this one here is d of a of x, or function a just inside function d. Function a being x plus 3, function d being 1 over x. The actual equation of this is 1 over x plus 3. It's 1 over x translated 3 units to the left. And that's the key. Now, again, if you were someone who hadn't really learned about graph of 1 over x, and we have seen it a few times now, that definitely makes this harder. Because once you know what 1 over x looks like, you can visualize that it's been moved 3 to the left. But it has to be this order. So a inside d. Last two. Let's see if I can do this without screwing up. If you look at this function here in green, it looks like the absolute value of x. And remember what I mentioned from a previous lesson, the absolute value of x can always be thought of as, or the absolute value of anything, can be thought of taking a number and squaring it and then square rooting it in that order. Well, once I do that, I can look at my choices and I realize this is function b inside function c. But again, the order matters. Notice, what if I had this the other way around? What if I had y equals c of x inside b of x? What if I did that? Well, c of x is root x, and b of x is u square. This is not the same thing. If you square root something first, you can't even have negative values there. Remember, you can't square root a negative number, and it's not a real number. It's an imaginary number. And again, I don't even want to get into that in this course. And so this and this are the same operations, but in different orders. And if you have a value that's squared and then square rooted, it's always the same as the absolute value. You can take any number and square it, but you can't take any number and square root it. And so this example here is not the same. In fact, that example here is what we see off to the right. What I have off to the right here in purple, this is the graph of the square root of x then squared. Because this graph doesn't even exist when x is negative, and that's because when x is negative, you can't even square root it, so there's nothing more you can do with this function. It's not until you get to 0 that you can start to actually input values into this equation. And so this is the other way around. This one is b of c of x. And in general, I would recommend you kind of make note of what I just kind of commented on. So I'll just make a little note here, and then I'll finish it all off. So in general, just to make a note, if you take any number, any value, and square it, and then square root it, that's the same as the absolute value of x. If you do it the other way around, if you take a number and square root it and then square it, it's not the same as the absolute value of x. It's not even the same as just x, because if you write this, that implies that if you put a negative number into here, you'll get the same negative number out here. It's only the same as x as long as you're not putting in negative numbers. If you put in negative numbers, you can't even substitute the value in. And so the way to make this correct is if I square root x first and then square it, it's the same as x with a little note, as long as x is greater than or equal to 0. And so what you have here is always correct. And If we're just thinking about positive numbers, yes, 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 these two are the same. It doesn't matter what order you perform these operations. But that's ignoring half of all numbers. Never a good idea. But yes, if you just think about positive numbers, it doesn't matter what order you perform these two operations. But once x is negative, then it definitely matters. And now I'm done. Phew, only made about 17 mistakes.